And this is a very special session. This is a session in which we honor our young colleagues. It's a session where we present the awardees of the MERAC prizes for early careers. So I'm just waiting a little bit that people take seats. So my name is Nabila Aganim, and I have the pleasure to have been entrusted by the EAS Council to chair the prize committee of the EAS. And it's my real pleasure to be chairing this session together with Lucio Mayer, our colleague from Zurich University, who is representing the MERAC Foundation.
Yes, so I think you can hear me because I also have a mic.
Sorry.
Yes, so it's really a pleasure to be here. As Nabila is saying, I'm representing the MERAC Foundation. I'm the scientist in the MERAC board, and we also have another member of the MERAC board here, Jean-Marie Louzier, who is also coming on stage. So it's a pleasure, as always, for the MERAC Foundation to be able to award these prizes and support young scientists in Europe.
And you may know, and if you do not know, we tell you that the MERAC Foundation is awarding prizes every year, and every 2 years it's for early career scientists, which is this year's ceremony. The MERAC Foundation also awards prizes for the best PhDs. This will be next year, and we'll tell you about it a bit later. So we're very happy to have 3 outstanding awardees this year. 3 prizes, one for theoretical astrophysics, astronomy, one for observational astronomy, and one for new technologies and new messengers. And these are the 3 awardees that you will see, that you will have to meet, that you will meet, and basically that will hear their talks. And we will start first with Johan Samsing from the Niels Bohr Institute, who's been awarded the MERAC Prize for Theoretical Astronomy. Please, on stage.
So yeah, it's a really a pleasure. So it's a pleasure to award Johan Samsing the MERAC Prize in Theoretical Astrophysics for early career for his seminal contributions to the understanding of how binary black holes merge in the universe. Congratulations, Johan.
Thank you. Thank you.
The stage is yours.
So the stage is yours now, and you're going to tell us about how to probe the origin of gravitational wave mergers. You can either use the mic there, or I can hand you mine.
Yeah.
Fair enough. Here it is. 25 minutes.
Good.
I'll take this so that you don't forget.
Yeah. Okay, welcome everybody. I'm Johan Samsing, and I have been puzzled about this problem of how to probe the origin of binary black hole mergers since we saw the first binary black hole merger around 10 years ago. And during this talk here, I will give you just a brief overview of the field in general, and then I'll go into a little bit more technical details. So this is the first talk during this session here, so I hope that you will be able to put some time into your working your brain a little bit on some simple estimates for how binary black holes are merging our universe with what we will call pen and paper estimates to show you how many of us theoretical astrophysicists are working actually. And then I will finish with some of the new ideas and open-ended problems and show where we are today. So probably many of you, I'm sure many of you have seen this figure here. Here we see the 2 binary black holes, or the binary black hole, the 2 black holes, the first observation that we see up on the screen here. And the gravitational wave signal we see to the left, and you should read it as you're going from left to right. You're going from the early inspiral phase towards the merger phase. You have the ring down, you have the burst, and that's the gravitational waves that you see with, for example, LIGO and Virgo. And the big question is, what can we learn from these mergers, right? So if I'm showing a few of these figures here, so here I have a few gravitational wave signals. And you can see the difference here is that they're lasting for different periods inside the LIGO band. And the one that have a fewer cycles lasting for the shortest times are the most massive ones, right? So you can see with gravitational waves, you can at least measure the masses of the black holes. Now this here shows a distribution of some of the waves that we have seen so far with the LIGO. Now we have seen about 100 binary black hole mergers, and we will, 04 is soon coming out, and we will have a few hundred more binary black hole mergers. And what we can measure from these gravitational waves are the black hole masses, as I just showed you, with essentially the number of cycles. Then we can measure the black hole spins. And the reason is that when the binary black holes, if they are spinning, they will also couple to the orbits themselves as they're moving around each other. That coupled system will make the orbit wobble a little bit, and that wobbling we can see in the gravitational wave signal. And then we can measure this called the eccentricity. So if you have two black holes in a perfectly circular orbit, you will have this fine sinusoidal signal. But that's not the case if the orbits are completely eccentric. Then when they're coming close at pericenter, they will send out a boost of gravitational waves. So it's very easy to tell the difference between the different orbital types. Now, there are many different correlations that you can make of mass, spin, and eccentricity. Here I'm just showing the mass plot here. So what you see here in the bottom are one of the main questions that are easy to look into once you have the estimation of the masses at least is, do we have black holes that are forming very close to the neutron star mass? And do we have binary black or single black holes that are forming up what we call the mass gap, about 45 to 50 solar masses, right? So those are the questions that, at least for these mass figures, that we are trying to answer. But there is much more information hidden here, and I'll get into some of that very soon. So the big question now is, how and where do these binary black holes form and merge? As you know, if you have a black hole, there's no way to tell how it's formed. It can form through many small mergers that came in, formed the black hole. It could have been eating up gas. It could be primordial black holes. It could form from stars. It could be formed many, many different ways. Just looking at the black hole is impossible to tell. It's only specified by the mass, spin, right? So we have to find other ways. But we are, of course, not guessing completely in the blind, right? So let me go through a few of the channels that we think might be operating. Maybe the binary black hole merger forming in the galactic center. In the galactic center, we might have not just our own, but in general, you have supermassive black holes, high densities. Black holes can come in, scatter off each other, possibly merge. You can have gas, you can have star formation. Many processes can happen that could bring black holes together and merge. You can also have stellar clusters. We see them on the sky, about 150 globular clusters we have in our Milky Way. And if you have black holes in these clusters, they will scatter off each other and potentially merge. And if you look out at the night sky, you will see a lot of stars. What most people don't know is most of them are actually binary stars. Easily imagine that if they actually turn into black holes, you immediately have binary black holes. You just need something for them to merge within a Hubble time. And that could be, for example, a third companion, as I'm showing here. Or it could be something else. So we have to try to understand how do we differentiate between these different proposed channels while keeping something else open, right? So this is one example how you could do it. You just take a look at the clusters. So here I'm having the first line here. And then the second panel here, I have the isolated binaries. So if you have binary black holes that are forming in clusters, the spins are probably not correlated. They just encounter each other randomly. So the spin distribution will be isotropic or random, right? Where if you have isolated binaries, they're probably correlated because they formed out of the same cloud or disk, right? And same arguments you can do for masses, and you can do it for the eccentricity. So these general properties you can map to different channels. And people were thinking about that, 10 years ago. We were thinking, oh, we just need, 5 to 10 binary black hole mergers. If the spins are all correlated, we know it's binary stars. But right now, with more than 100 binary black holes seen, we still have no idea of where these binary black holes are coming from. People are figuring all kind of power laws and this and that, and it has, giving us a little bit of information, but we still have no idea. And there's no reason to think that with 100 mergers more, 200 mergers more, that we would be able to make any breakthrough in this. So we need new ideas, right? And here in the next, 20 minutes or 15 minutes, I will bring you through. Now we're going to get a little bit more technical, but I'm just going to show you how many of you also will be able to contribute to this field. Sometimes when I'm talking to younger people, they're saying, oh, there's so many people working in this field now. How should I be able to do this and that? And people have been writing in-body codes for decades. And how should I? Now I'm going to show that the way that I got into this field was just a few pen and paper calculations, and that kind of opened up a lot of interesting stuff that people have not been thinking about. And I'm sure that there are many more open questions out there that many of you could also explore, maybe using similar ways of thinking. So let me just take you through how you can do this. So now we're going to split it into two parts. We're going to learn from, try to see if we can figure out where the binary black holes are coming from the distributions. As I talked about, we could have a distribution of binaries, but there could also be perturbations to the gravitational wave signal. I will come to that later. Let's start with the distributions. And now I'll tell you, get you through this problem of how to probe the different ways binary black holes can form and merge in these actually very, very complicated in-body systems. You have 100,000 of stars, black hole with different masses, and then see if we can make some progress just using some logical steps here. So the question now that we are after, we have to ask the right questions now. Where are the black holes in this cluster? Question number one. How do they interact? How do they merge? And can we probe their origin? Is there something special about the mergers? There are different methods. You can do the in-body method. It's very, very expensive. Everybody here is going in cube, right? In squared. If you have a lot of stars, which you have in clusters, there's no way you can do it. You have to come up with other ideas. People have been doing that for decades. You do Monte Carlo simulations. You use the potential of the cluster and then sample the orbits, right? Well, it's the same. You don't, like, if you want to figure out where the Earth is around the sun in half a year, you don't have to solve Kepler's, you don't have to solve the in-body problem. You can just multiply some different timescales using Kepler's equations to figure out where the sun is, right? And the same you can do with more complicated systems. And then there are analytical methods, and this is what we're going to go into now. So we're going to go through a few relations to show how we can actually make progress in this field here. Where are the black holes? Now, first of all, we're going to make use of a very simple observation that normally takes place in many kinetic systems. That is energy equipetition, right? So when you have objects that are interacting, they tend to share energy. If you have that in the cluster, you can see here that if I equate these two energies here, if there are black holes that are more heavier than the other population, say the stars, they will move slower. They will naturally therefore sink to the center. So we have a picture where we have a distribution of black hole stars, the smaller black holes, where all the heavier black holes fall to the center, and we essentially have this picture here. So now we have figured out where the binary black, or where the black holes are, right? And the black holes, since we can see that the segregated mass as a function of the radius, the most massive in the center, the black holes always tend to interact with other black holes that have similar mass. So we can make the assumption that binary black holes or other kind of systems generally interact with similar masses. So now we have massively reduced this problem to something that we might be able to do some progress on. Now we just have to figure out what kind of interactions that could happen in this cluster here. We see binaries all over the place, so why not think about there could be some binaries. The stars we just see as a fluid, right? And that's keeping the black holes in the center. We already talked about that. The single interactions is essentially what I showed you just before. That gives this exchange of energy, keeping the black holes in the center. Then we could have binary single or binary interactions, and the gravitational wave evolution we will come to in a moment. That's what we call our mergers. So now let us try to focus on how many binaries and what kind of binaries might be in this cluster here. Now this here is a typical scattering. You have a binary that interacts with something else, okay, before and after. Now I'm cheating a little bit because I told you I wouldn't show any in-body stuff, it's just pen and paper. But these results have been around for the past 50 years, so this is not something that I came up with. If you're doing a triple scattering, you'll find something like this, right? So it's a highly complicated system. But what would happen is that on average, the binary will shrink its semi-major axis, and you can easily understand why that's the case. We don't need in-body simulations for that. Say you have a binary and a third object is falling from infinity towards the binary. We know the triple system is an unstable system, so the only way that it can split apart is sending out the single back to infinity. There is no way that that could hit exactly energy zero again, so it will always give it some excess energy to kick it out to infinity. That means that the semi-major axis have to shrink a little bit. You can think, does it have to shrink by a constant factor? Yes, it will, and the reason is that the Newtonian in-body problem is a scale-free problem, meaning there is no way you can tell what the masses are of these objects, I can always scale my system up and down with a proper n-body units. That's shown down here. So the acceleration I can scale in some units, some m prime and r prime, or in some different units. But when I put in GR terms, I will have a different factor on my acceleration terms here. So this is the one taking into account gravitational wave radiation. And this factor here, gm over r squared, is this post-Newtonian weight factor. M is the characteristic mass of my system, R is the separation. So you can see I cannot change the things independently when I have GR. GR is not a scale-free problem, but in Newtonian gravity I can do it. But you can see that the only thing I can change here, the only scaling I can do is if I'm keeping M over R fixed. So if I'm scaling both of them by the same factor, the whole n-body problem will remain the same. And that makes sense. That's the same as redshifting the system, and we know that that's perfectly fine in the GR. So let us take a look at how much energy that is released, one of these scatterings. So you take just the Newtonian, this one minus this one, so the energy after, or the semi-major axis after, and you see here the energy released is 1 over A, where A is the semi-major axis. Let's change that into an energy flux instead. So you can see here, so if we take the energy flux, E dot, and we take the energy that's released over one scattering here, related to the characteristic time scale that it takes to release this energy, which is the time it takes for other objects to come in and interact with that binary. And that interaction time scale is 1 over n sigma v. N is the density of objects in my cluster. V is the velocity dispersion. Sigma is just the Newtonian cross-section for two objects to meet each other if they fly past each other. It's very simple, and it goes as proportional to A. So you can see here, if I'm putting it in, I have E dot proportional to these two factors that cancel. So the energy production of my binaries inside the cluster is constant, right? So the binaries act as a constant heat source inside my system, right? And for that, I need energy balance. If you're counting out how much energy that I have in my cluster, you will find that you can only have a handful of binaries at maximum at any given time. Otherwise, I will blow up the cluster. So the problem has now been reduced to only a couple of binaries and possibly 1,000 of black holes, 100,000 of stars. And now, so the most relevant channel that we have to look at are binaries interacting with other singles. So now we have to identify the different way that a binary can merge inside the cluster. That's the last step in this process here. It can either merge inside the cluster while it's waiting for something else to come in and interact with it. It can also merge while it's bound to something else. You saw these crazy interactions that I showed you. It can also merge doing that one. And it can also merge within a Hubble time if the binary is being kicked out of the system. And to each of these, we have a characteristic time scale. The two-body time scale, which is the interaction time scale, the three-body here, which is the orbital time of my binaries, and the ejection time scale, which is the Hubble time. If the merger time is smaller than any of these characteristic time scales, my binary in question will merge. Okay, so this is the merger condition, merger time less than this characteristic time scale for these three different outcomes that I've been looking at here. So the last step is to calculating the probability for that to happen. The only equation that we have to take from somewhere else that we couldn't, just sit down and write on a piece of paper I've been doing with the other things is the Peters equation that tells you what is the merger time of two black holes as they are spiraling in due to gravitational wave radiation. T naught here is the merger time if the eccentricity is strictly 0, and this here is the correction from the eccentricity. By combining distribution of binaries as they're floating around in this fluid here, we can combine the probability that a binary will merge within a characteristic time tau, and that follows directly from this equation here, and we can now find that the probability that a given binary merge within time tau is proportional to tau over T naught. The T naught is the, as I said, the merger time, assuming the binary is not a circular orbit, to 2/7 power, and that's because you have a sampling in eccentricity. So far, I have not done anything else than just looking at the statistical properties of systems that are interacting in a cluster. Maybe we don't know T naught and we don't really care about the absolute probability, but we care about it relative to like the different probabilities relative to each other. Right? So if you have a binary black hole that's kicked out of the cluster, it will differently contribute to the merger rate. So now we're going to say, what is the number of mergers that are forming inside my cluster relative to the one that are kicked out? I can plug in the numbers, and I find about 40% of all my binary black hole mergers forming inside the cluster. About 10% are forming doing these triple scatterings. And now I'm just going to show you how one of these looks like. This here is a triple scattering, and one of my binaries are forming, actually merging, doing my triple scattering here. And if you're comparing the timescales, I'm not sure, but this is exactly the same arguments here, you'll find basically all of these are highly eccentric. So clusters form about 5 to 10 highly eccentric binary black holes. This might seem trivial now that I'm talking about it here, but nobody was thinking about this about 5 to 10 years ago, right? Despite looking into this problem for decades with Monte Carlo and in-body codes. So this illustrates one way of thinking where you can make progress. And there are now hundreds of people working on the eccentric waveforms, trying to understand where these binary black holes are coming from. Here I am showing, here I'm cheating a little bit. Here I'm sampling from the distribution I showed you here. And I also calculate the strain, and I show you where the different strain tracks for my 3-body mergers during my triple scatterings, the 2-body mergers, the one that are merging in between my scatterings, and the ejectors one, how they distribute here. So the 2-body mergers will be eccentric at LISA, the 3-body mergers will be eccentric in LIGO, and this here is an actual interaction tree that was found from one of my friends, Carl Rodriguez, who is doing the Monte Carlo simulations. So with this process here, I calculated a few years ago, 10%, as I said, will form during these triple scattering to 5% are highly eccentric in the LIGO band. I could put that in the closed form calculations, which I showed you some simplified of here. And shortly after, groups that are doing Monte Carlo in-body simulations found the exact same number. So right now, eccentricity is now one of the most reliable ways of identifying a dynamical formation channel. So there's a lot of work being done in that right now. Now, does nature give us any hint of what's going on there? So can we use it for anything? Isabel Rosemary Shore, that I'm working with also, she's been doing some wonderful work, and here she shows the estimated eccentricity for different gravitational wave events here. And there's a few here that stands out. Now I'm just going to give you one example of how we, with this very simple way of thinking, try to learn from these systems, right? We're now going to take a look at this 1905-21. The binary black holes were very, very heavy. There might be an EM counterpart. I'm sure that Nick or Matt, he will feel a little bad when I say that. It is not entirely clear if there was an EM counterpart or not. But it also did show that there might be some eccentricity. So we were thinking, what kind of systems could it form in? We are thinking about these very active galactic nuclei, disks that are in the center of galaxies. Why? Because you have a lot of gas that might be able to produce some light, one way or the other. At least you need something that is not just vacuum. High masses, possible you can get from mass accretion, and then you have the eccentricity, and there was kind of puzzling how we would be able to get eccentricity and all the 3 things at the same time. So we took basically the equations that I talked about and looked at what would the probability be for these highly eccentric mergers if I consider a planar configuration relative to these isotropic clusters. And interestingly enough, you will boost the probability by almost 2 orders of magnitude, such that you almost can reach the order of unity of highly eccentric mergers if you consider things in the planar geometry. So there is a lot of people working on trying to understand these signals from these AGN disks as well. And nobody at that time have been thinking about that, and that also opened up a lot of new studies, and we were it is always a matter of timing, and we got this paper here in Nature. So I will finish with, during the last 3 to 4 minutes here, I will finish with basically the problem that we are facing right now. And the problem we are facing right now is that now I have showed you a few different ways that highly eccentric mergers can form, and you have masses, and mass can, the mass can change due to gas accretion, this and that. So eccentricity is not just the stamp of what's happening in a cluster. It can form in many, many different ways. That brings me to this perturbation part here. So I have a couple of slides about this, and then I'm very happy to talk much more with many of you because this is an extremely rich topic here. I'll just briefly go over some few things here. Imagine you have a binary in gas. It's not vacuum. The gas will exert torques on this binary, so you will have perturbations to the signal that you don't expect in vacuum. You would also have it in these binaries that are forming in my triple scatterings. And the reason is the following. When you have a binary that's merging on the curved orbit relative to a reference binary here in vacuum, so now I'm trying to probe if there's something nearby. If I'm sitting as an observer down here, I will see a time lag between the curved orbit and the reference binary. In physics, we sometimes call that the retarded time. It's proportional to a half AT squared. So if I can measure this retarded time, which will just show up as a phase shift, I think I have a figure here. It will just show up as a phase shift here in my signal. I'll be able to measure the acceleration or exactly what is the space-time doing around my binary black hole as it's merging in. I quickly skipped over this one here, but there's nothing weird in this way of thinking because people have for decades doing this with pulsars. That is how you measure properties of binary pulsars. You're looking at the pulse modulation. We have now made tools that you can do exactly the same with binary black hole mergers. Looking into the perturbations of the gravitational wave signal, we can go in and probe the origin of individual binary black hole mergers. Nobody thought was possible just a few years ago. And we have shown that to be possible using some new numerical things that I've been working on. The idea is that you simulate the whole thing forward with gas, GR, third objects, everything. You switch it all off, you take the binary, simulate it backwards in time, put your observer, and look at the differences between the forward evolution and the backwards. And that has opened up a completely new class of binary black hole mergers that have huge perturbations. We see them all the time in the clusters. We can see them in the HN disk. We see modulations from gas. We see modulations from the supermassive black hole. So there's much more information in these gravitational waves than what people normally thinking about mass, spin, and eccentricity. And I will finish here with the statement of that we will be able to probe the origin of individual binary black hole mergers, and it is my great pleasure to invite you all to the Niels Bohr Institute, not at the same time, but here I have a fantastic group that are doing a lot of great work. We are organizing many schools, workshop, PhD schools. If any of you want to get involved or want to come and visit, just come and talk to me. This year was just some general, sparks of what we have been interested about the last couple of years. But I'm always open for new ideas and new people to talk to. So thank you.
Thank you. Oops. Yeah. Can I have this? Can I have? Oh, thank you. Thank you very much for this great talk. It looked like it was easy to handle. So thanks a lot for the effort in pedagogy. And now the floor is open for questions. Oh, you have questions. Okay. Don't escape. So are there questions in the audience? I see one there.
Thank you for the talk. Is the mean field, like when you're dynamical capture calculations for the binaries, is the mean field from the globular cluster or from the star cluster important as well? Is it something you need to consider?
Very, very good idea, very good point. People have been looking into this, and this, as I'm saying here, if you just compare timescales and you don't have to spend like years calculating this, you can easily see that it's not important. The mean field will show up as basically modulations to the binary properties as you would have in these quasi triples as people have been talking about, right? And if you calculate, the quasi timescale is billions of years.
Okay, thank you.
So it's not important. It could be in nuclear star clusters where the density is much, much higher.
Thanks a lot. I think that there was a question here. Yeah.
Thank you very much. It was a fantastic talk. I was wondering, do we have an estimate of strands for natal peaks for individual black holes forming in such dense clusters?
Oh, if we have what?
The estimate of natal kicks for this.
Natal kicks, yeah. Well, so the natal kicks, like you're talking about when they're forming, basically.
Right.
So all of the binaries that I'm talking about here has nothing to do with the primordial binary properties. So it is actually binaries that are forming while the cluster is evolving. And it is all due to this energy balance that I'm talking about. So if you don't have any binaries, the cluster will start doing like this. So you kind of need an energy source to bounce back. So the cluster by itself generates this heat source that I was talking about, and that's why you have this balance of heat exchange from the outside to the core parts.
Okay, thank you.
Thank you so much. I think that there was a question here and then another one in the back.
So for the perturbation signal, given the noise and sensitivity of LIGO in 04 and 05, do you have an estimate of the distance to the source within which that is detectable?
Well, okay, I can always cook up a problem where something is very close by, you can easily see it. I would maybe say that there has been one paper on the archive, it has not been accepted yet, but it's very, very interesting. It's a group from the Shanghai Observatory, I should have shown it here, but they claim to have seen acceleration, one of the binary black hole mergers that LIGO have seen so far. And they see, it seems to be consistent with a binary black hole, as I remember, maybe around an IMPH like 10 to the 4, 10 to the 5 supermassive, or black hole. It could be in a disk, it could be something else. So you can, just as my final comment here, so the acceleration that you're basically probing is going as 1 over r squared, right, with r as a characteristic distance. So you don't have to change things much to see massive improvements in these perturbations that you're gonna see. So I can easily come up, cook things up that will motivate you to look for this right away.
Yeah, so there was a question there in the back.
Hi, Kaushik Shen from the University of Arizona. I have a naive question about the modeling the waveform of these mergers, eccentric mergers. Like, how easy is it to disentangle, say, eccentricity from like effective spin and the mass ratios of these binary mergers?
Maybe you already know the answer to this since you're asking. Since it is very difficult, and especially the spin and the eccentricity that seems to correlate. So actually this study that I showed up here by Isobel, she did the absolute best thing that she could do, but it was for line spins. Now they're working on misaligned spins with eccentricity, but once you start to play around with the spin, you have infinitely more things you have to vary. So you have to be smarter, and people are working on it.
Thank you.
There is time for one last short question, if there is. Are there any hand raised? There is one there.
Yeah, thank you so much for amazing talk. So this is just maybe a little bit open-ended question, but like we see that galaxies that just recently merged, they have enhancement of the tidal disruption events. So my question is, do you imagine that the transient times or like some changey times in the population, such as mergers of galaxies, can also lead to enhancements of gravitational wave signals?
I did think about this myself a few years ago, and I think it's still a very interesting question. So we should maybe think more about that. Yeah, right. It's a very good point. Yeah.
Thank you.
Thank you so much. I think that Johan owes another round of applause.
Thank you.
And we're now going to welcome Matt Nicol on stage, who is the awardee of the Observational Astrophysics Merak Prize from University Queen's Belfast.
So it's a pleasure to award the 2025 Merak Prize for Early Career in Observational Astrophysics to Matt Nicol for his work on explosive transients, compact object mergers, and tidal disruption events. Congratulations, Matt.
Congratulations. So the stage is yours. I'll take it so that you don't forget it. And you can have the mic. And the presentation title is here, Golden Age for Explosive Transient.
Help if I could get this on. There we go. Okay, fantastic. Well, thank you so much to the Merak Foundation and the EAS, both for the very kind award of the prize and for the chance to speak to you all here today. Thank you all so much for coming out as well. It's really special for me to win this award in Cork too. It's really nice to have EAS on the island of Ireland where I grew up and where I currently work. So it's really fantastic to see you all here. There's also a million other people I should thank that have helped over the years. This is a very, very collaborative field that we work on, these transients. I don't have time to name individuals, but a lot of institutions and a lot of collaborative surveys that we've worked on together, as well as the people who funded me over the years. I hope that you know who you are, and thank you very much. So I've promised to talk about the golden age of explosive transients. So first of all, let me define what I mean when I say transient. So this is basically any source that appears kind of suddenly, it reaches some peak in its brightness, and it fades away, usually never to be seen again. And these are explosive transients connected to usually the destruction of a star. So there's a huge amount of energy that's released in these processes. I find the physics of these explosions to be really fascinating. But what I want to convince you of today is that these explosions also help us to solve many other really interesting problems more broadly within astrophysics. So that's quite a big claim. To call this a golden age is also quite a big claim because this field goes back a very long way. So people have always looked up and seen new things appearing in the sky. And historically, these are mostly local supernovae within the Milky Way. You could see them with the naked eye. And we saw them thousands of years ago, and today they've left behind beautiful remnants that look like Cassiopeia A here. Of course, then in the 20th century, with professional astronomy and large telescopes, we started to find these kinds of transient events occurring throughout the universe. So this is a pretty typical example, though not a typical image. This is a beautiful Hubble image of a supernova explosion here occurring in the spiral arm of this nearby galaxy. So searches for these kinds of transients in other galaxies and surveying them over time to see how they evolve, people were able to put together a pretty good basic picture of the physics behind these explosions. So this is the kind of supernovae in a nutshell. So what happens that we actually get to see when we observe this light? So the star, first of all, is unbound by a blast wave that goes out through the stellar envelope that destroys it. The typical energy involved in this blast wave is something like 10 to the 51 erg, so a huge amount of energy that gets deposited by this shock. So the first emission that we see is the expansion and the cooling of this shocked stellar envelope. But unless the star is very, very extended, that emission fades away pretty quickly, and a different power source takes over to produce the bulk of the emission that we see. So most supernovae are actually powered by these radioactive decays. So in the center of the explosion, the conditions are very hot, very dense, you get a lot of nuclear fusion, and you make lots of elements up until the iron peak. And that includes a lot of radioactive 56 nickel. So it's the radioactive decay of this nickel that drives most of the emission that we see from supernovae. On longer timescales, the decay of the daughter nucleus, 56 cobalt, to stable iron produces emission that we can monitor then over the coming months and years. So within this picture, essentially it's diversity in the amount of explosion energy, the amount of nickel that you produce, usually between a few hundredths to a few tenths of a solar mass, as well as differences in the size of the star and its mass that lead to differences in the observable characteristics. So we can parameterize this with our light curves. We can measure the characteristic timescale, how long does the transient last, as well as the peak luminosity of that transient, and plot those two things against each other, and you get a very broad diversity of transients with very different timescales and luminosities. So within this, we also see certain like-minded events, like the cluster together. So you can see different clusters within this diagram. To understand physically what these clusters mean, what kinds of stars are producing them, we need some extra information. For that, we need to use spectroscopy to find out what these transients are actually made of. So historically, we've done this by looking at a supernova spectrum, identifying which elements we can see in the spectrum, and using that with this very simple flowchart. So initially we asked, does the star show hydrogen at the time of explosion, or has the hydrogen layer already been removed? If the hydrogen's gone, we ask, do we see helium, or is the helium also gone? And these two simple questions kind of just come from this basic onion skin structure of a massive star, right, with less massive elements towards the outside and heavier things towards the center. And those two questions define the three basic types of core collapse supernovae. So type 2 supernovae that still have hydrogen envelopes, types 1b and 1c supernovae that have gradually lost those outer layers. We think that these come from massive stars, more than about 8 times the mass of our sun, where the core has collapsed to make a neutron star, or perhaps occasionally a black hole. Type 1a supernovae, the other sort of historically famous class of supernovae, are quite different. We think, well, we're pretty sure these come from explosions of white dwarf stars in binaries where they either merge with or accrete from a companion until they become unstable. And their spectra look a little bit different with heavier elements like silicon, sulfur, and iron. So even within this very well tried and tested picture built up over many, many years, I would say there are still pretty enormous uncertainties that we are trying to figure out the details of. So if we take the most common ones by volume, these red supergiant explosions with extended hydrogen envelopes, we see red supergiants in the universe with a very wide range of masses, but we almost never see supernovae with masses above 20 solar masses. We don't know the reason for that yet. If we turn to the ones that have lost their envelopes, the types 1b and 1c supernovae, we don't know if some of those lose their envelopes because they're very massive stars with very powerful winds, or whether they're all stripped by binary interactions. And perhaps most concerningly, the type 1a supernovae that we use to measure the expansion rate of the universe, a cornerstone of cosmology, we don't even know whether the secondary star is another white dwarf or whether it's actually a non-degenerate main sequence star or red supergiant. To try and answer these big questions in stellar evolution, we turn to wide field surveys. So this has been sort of the defining thing of the last 15 years. So these wide field surveys essentially are robotic telescopes that have very wide fields of view, so you can cover several square degrees in a single pointing, and you use that to image the whole sky essentially every 1 or 2 days. Currently, the most productive surveys are probably ATLAS and GOTO that use 0.5 meter telescopes, and PanSTARRS and ZTF that see fainter transients with 1 to 2 meter class telescopes. And of course, on Monday, we all saw the first look images from the Rubin Observatory. This is good, it works, after all this long wait. This is going to do the same experiment, but this time for the first time with an 8 meter class telescope. So this will see really faint things, but still probe a very wide field of view and therefore an enormous volume. So we find a lot of transients with this technique. These days, we find about 20,000 new transients per year. So we're actually off the scale of this plot. This is very exciting, of course. We want to find more things, but to actually understand them, we do need to get spectra of as many as possible. So surveys like PESTO on ESO's NTT telescope, as well as the ZTF Bright Transient Survey, have got spectra of thousands of these transients. You can see almost all of them are type 1a and core collapse supernovae. But also you can see, as time has gone on and we've got better at finding transients, it gets harder and harder to keep up with spectroscopy. This is even before the fire hose of Rubin turns on, so this is going to be a big theme of the next few years. However, with the few thousand transients that we have spectroscopically classified, we already see way more diversity than the simple picture that I've shown you that we built up over the 20th century. So what I want to do now is take you through the new landscape of transients. We're going to say goodbye to this simple picture. And we're going to see a much more complicated flowchart. So here's my best attempt to put a modern version of this together with all the transients that we see today. Okay, that's the reaction I wanted. Yeah. So don't worry, I don't expect you to follow this flowchart and certainly not to memorize it. I just want to highlight some key bits of information that we use now to understand what kind of transients are out there. And I want to really emphasize, this is not stamp collecting. We're trying to use these different clues to figure out the actual physics of these explosions and use them to solve bigger problems within astrophysics. So what do we look for these days? So we don't just look at hydrogen, helium, and silicon anymore. We use all kinds of rare elements, as well as looking at the ionization states of those elements to probe the temperature. We look at the shapes of lines. Are they narrow or broad to tell us are things moving fast or slow? We look at other non-optical signatures, for example, X-ray and radio emission to probe non-thermal processes. And if we're really lucky, gravitational waves to probe processes that we just can't see with electromagnetic waves. And we look at the location of the transient as well as the transient itself. So which kind of galaxy did it happen in? Where within that galaxy did it occur? And from these different clues, we've realized that not all transients come from massive stars or white dwarfs and binaries, but there's all kinds of progenitor systems out there. So we find lots of transients now associated with supermassive black holes in the centers of galaxies and compact binaries of neutron stars with another neutron star or a black hole. And lots of new classes of transients then have fallen out from these great wide field surveys. I'm not going to go through all of these, of course, but I want to highlight a few key examples. I mean, an obvious example where this diversity is very exciting is within the type 1a supernovae. These were the famously homogeneous type 1a supernovae that we can use to measure distances. It turns out there are lots and lots of subclasses of these things. Understanding the physics of these different subclasses can really help beat down the systematics when you make your supernova Hubble diagram. But I want to focus on 3 kinds of transients here that I've worked a lot on over the last 10 years, and especially what they can tell us about bigger picture questions within astrophysics. So first of all, when you find a new type of transient, the first thing you ask yourself is, can our current picture of stellar evolution actually accommodate the thing that we're seeing? So a great example here, where this was not the case, is superluminous supernovae. So these were discovered in the early days of wide field surveys about 15 years ago, and they look something like this. So you can see normal supernova-like curves here, and then a small fraction of objects, maybe 1 in 10,000 supernovae, or 1 in 1,000 supernovae, is both several orders of magnitude brighter, as well as several times more extended in its duration. So if you add up all the energy emitted in the optical by these superluminous supernovae, it's thousands of times higher than conventional supernovae. So you can't explain that with standard decay of radioactive nickel anymore. The other interesting thing about these objects is that they seem to have also lost their outer envelopes. These are hydrogen per and helium per stars. And that makes it very difficult to come up with an explanation for what these things could be. So we've basically spent the last 15 years now arguing back and forth about what the power source of these things could be. The two main models are that either the core of the star is very rapidly rotating, and this injects energy into the expanding debris, or the star is colliding with some pre-existing medium that turns kinetic energy into luminosity. In both cases, stellar evolution models really struggle to predict how this would happen for a hydrogen per star, right? How do you remove the envelope of the star while keeping it rapidly rotating? It's very, very difficult. Or how do you put several solar masses of oxygen right next to your star at the time of explosion? Both very difficult. So these are telling us something very, very interesting that we don't understand about stellar evolution. So one other very interesting thing about them is that they may come from some of the most massive stars that are out there. So if we try to infer from these light curves how much material was ejected, this is roughly the carbon-oxygen core mass because they've lost their envelopes. You can see this distribution extends up to maybe 30 solar masses or something, which is 10 times higher than the masses of conventional core collapse supernova cores. So these are potentially coming from enormous stars. These stars are rare, they have short lifetimes, so superluminous supernovae are a way to probe this very unexplored regime of massive star evolution. And what I think is even more exciting is that they seem to happen almost exclusively in dwarf galaxies. So here's a picture of actually a Milky Way and LMC analog here at a redshift of about 0.1. And the supernova did not occur in the massive Milky Way-like galaxy where most of the stars are. The supernova occurred in this little dot of a galaxy over here. And what I think is really cool, actually, as an aside, these images were obtained 2 and 3 years after the supernova, and it's still by far the brightest thing in this galaxy. So why do they happen in low metallicity galaxies? Well, I've just answered the question. Why do they happen in dwarf galaxies? Low metallicities, right? So we think that these galaxies have a very low metal content compared to other massive galaxies. So superluminous supernovae are happening because of some process in stellar evolution that can only happen at low metallicity. This is very interesting for understanding the early universe, right? Because we think the early universe was much more metal per. So these might be a local analog to understand star formation and stellar evolution in conditions more similar to the early universe. And because these explosions are so bright, we may actually detect some from the early universe and probe the first generation of stars directly. The second area I want to kind of talk about a bit that I get really excited about as well is how much progress we've made in understanding nuclear transients. These are transients in the nuclei of galaxies. So we all know that galaxies harbor supermassive black holes at the center most of the time. And historically, we've seen if those black holes interact with gas or stars, you can get interesting variability in the optical radiation from these galaxies. So of course, most of the time, what you're seeing is just normal active galactic nuclei flickering up and down, or supernovae close to the core of the galaxies. But these wide field surveys have unearthed a whole bunch of different kinds of variability that we never saw coming. I want to focus on one class, these so-called tidal disruption events, because there's a lot of interesting stuff that they can teach us. So what's a tidal disruption event? So basically, you've got a supermassive black hole in the center of your galaxy. A very unfortunate star passes too close to it, and the gravitational forces of that black hole destroy the star, form this long stream of debris, and the black hole starts to feed from that debris. So this produces a supernova-like flare, reaching roughly the Eddington luminosity of the black hole, so very luminous, 10 to the 44 ergs per second for a 10 to the 6 solar mass black hole. So we can see these previously dormant black holes halfway across the universe. And what's even better is that the shape of that light curve encodes the mass of the black hole. So we can actually use these to weigh the black holes in these distant galaxies. And what's really fun about these is that we never see them coming from black holes more massive than about 10 to the 8 solar masses. And the reason for that's actually quite straightforward. If you get more massive than that, the Schwarzschild radius of the black hole is so large that the star passes inside it before it's destroyed. And so we don't see any emission from inside the Schwarzschild radius. But this lets us use tidal disruption events as light posts to find low-mass black holes. Why is that important? Well, for a long time, we've been trying to understand the origin of supermassive black holes. How are they seeded? How do they grow? And to do that, we need to find the low-mass ones. So here's a very famous plot from Cormandy and Ho to show how the galaxy mass correlates with the black hole mass. And you can see nearly all of the data here is up here above sort of 10 to the 8 solar masses. And there's very few black holes down here at 10 to the 6 or 10 to the 7 solar masses. They're just difficult to find, difficult to weigh. Over here, this is a paper we just accepted a couple of days ago from our group. This shows the same distribution of galaxies up here, and now with tidal disruption events, 40 or so tidal disruption events added to this plot. So you can see the TDEs perfectly fill in this low mass regime that's almost impossible to probe otherwise. So one of my big hopes for the near future with LSST and other surveys is to find thousands of black holes in this regime and really pin down how these things evolve with their galaxies at the lowest black hole masses. And these are not just good probes of the black holes themselves, but also probes of the galactic dynamics that surround them. So much like superluminous supernovae, these TDEs show a strong preference for particular types of galaxies. A very large fraction occur in green valley galaxies or post-starburst galaxies. This is very surprising. This is only a small fraction of galaxies that pass through this very short-lived phase of galaxy evolution, but it harbors a lot of the TDE population. So the TDEs probe the central 100 parsecs or so of these galaxies so that we can use them to understand how the inner dynamics of the galaxies affect this large-scale quenching of the star formation that we see. So these galaxies formed a lot of stars about a giga-year ago and they've since stopped, and we don't really understand why. But it might be connected to the elevated rate of tidal disruption events that we see. So the reason could be that the centers of these galaxies are particularly dense or they've got very disturbed orbits with different morphologies. And perhaps these could be connected to the merger histories of these galaxies, which is, again, very difficult to probe. And interestingly, we've got at least 2 tidal disruption events from just the last few years that we've detected in actively merging pairs of galaxies. So this shows 2 examples here where you've got active mergers, and the tidal disruption event in both cases happened in the less massive galaxy within that merging pair. So this suggests mergers could be really important in inflating the TDE rate. And so understanding this TDE rate can tell us about the merger histories of these post-starburst galaxies. And this is on scales of hundreds of parsecs, but remarkably, we can actually use these objects to probe galaxy dynamics down to about 1 AU, which sounds incredible, but here's how we do it. So after the star is disrupted, it forms a disk of gas around the black hole. This accretion disk spreads laterally over time, and if you've got other objects orbiting the black hole with short orbital periods, eventually this disk spreads enough that those objects start to collide with the disk of gas from the TDE. So it's predicted then that once that happens, you'll get a flash of light every time this object passes through the accretion disk. And we think we've seen this process occur for a few nearby TDEs, which I think is really amazing. So this shows an example here of a very nearby tidal disruption event with very nice data, transitions to this disk-dominated phase with a constant optical luminosity for years, and then 4 years later, it starts to emit these huge pulses of X-rays every 2 days. So this suggests something with an orbit of only a couple of days around the black hole. So for comparison, the S stars in the nuclei of the Milky Way have orbits of years, not days. So this lets us probe the very central dynamics of these galaxies, right down to a regime where future gravitational wave detectors like LISA might be able to see these close-in orbiters. Currently, the rates of these close orbiters, completely unknown, but we can measure them with X-ray follow-up of TDEs. The last thing I'd like to talk about in terms of these new kinds of transients, I want to go all the way from galaxy evolution down to chemical evolution, because transients are also incredible probes of how we build up the different elements we see in the periodic table. So we know that supernovae are responsible for a lot of the nucleosynthesis, up to roughly the iron peak. We don't actually know exactly the ratios of these elements that come from massive stars versus white dwarfs. That's another interesting question. But even more interesting is once you get past the iron peak, to build up the heavier elements, you actually just can't do it anymore with nuclear fusion. At that point, you have to have a different mechanism. So here what you've got to do is bombard your nuclei with a very strong flux of free neutrons. And if we think where in the universe has a lot of neutrons, the obvious answer is a neutron star. And you can get those neutrons out of the neutron star by colliding it with another neutron star or by tidally disrupting it with a black hole companion. So if you do that, the prediction is that all these free neutrons will build up all these heavy elements, including famously where probably all gold is manufactured. And that informs the secret pun of my talk titled The Golden Age of Time Domain Astronomy. It took a while to get there. But the other thing about this nucleosynthesis, it produces a lot of radioactive elements, right? So as this radioactive ejecta is expelled, it'll cause the material to glow. So we see this as an optical transient. And we call this optical transient a kilonova. So trying to find these kilonovae now is a central goal of time domain astronomy because we can use them to probe how this periodic table is actually built up. However, this is very difficult to do. Kilonovae eject a very small amount of matter compared to supernovae, and that gives them a very short characteristic timescale. So if we go back to this plot from Atlas to show all the transients we found over the years, guess which one is the kilonova? Yeah, it's over here. It's the one that only lasts for a day. So it's very hard to find them with your wide field surveys and actually get the data you need to confirm their nature before they've already faded away. Luckily, there's other ways to find them. One way to find them is with gamma ray bursts. So what happens after the merger occurs is that accretion onto the remnant of the merger can drive a jet. If that jet is pointed directly towards the Earth, our gamma ray satellites can detect the emission from it. And that basically tells our optical telescopes exactly where to look to try and find the optical emission from the kilonova. So this has been pretty successful over the years. There's maybe almost 10 kilonovae detected with this approach. This is probably one of the best ones here from a GRB in 2021. But it comes with its own challenges, this technique as well. So you have to have a GRB jet pointed directly towards us, otherwise we won't see it. And you have to be very careful in disentangling the gamma ray burst emission from the kilonova emission if you want to try to measure the yields of different chemical elements. Luckily, there's a third way to find kilonovae without wide field surveys or gamma ray bursts. And of course, that is the one I've saved for last. The best one is gravitational waves. So this is one of the biggest success stories we've had in the last 15, 20 years of this field. You've all heard the story. In 2017, the LIGO and Virgo gravitational wave detectors found a gravitational wave signal from a neutron star merger at only 40 megaparsecs, incredibly nearby, localized it to a tiny patch of the sky of about 30 square degrees. And this gravitational wave signal was accompanied by emission at basically all wavelengths, from the gamma rays through to the radio. And all of the optical telescopes on Earth turned and pointed at this little patch of sky and confirmed that this was indeed the electromagnetic emission from this gravitational wave merger. So we all got incredibly excited. We pointed all of our telescopes at it and got phenomenal follow-up data. Here's an example of the light curve of this thing, from the UV to the infrared, from many groups around the world, sampled multiple times per night. And from modeling this light curve, the model fits overlaying here, you can infer things like the mass of ejected radioactive material. So from this model fit, we estimate that somewhere around a few hundredths of a solar mass of these heavy elements were ejected by this merger. So if you assume that that is representative of all kilonovae, and you assume that our current best estimate of the merger rate is roughly correct, and you multiply those two numbers together, you would infer that these things could be responsible for all the heavy elements in the universe. But that's subject to the big uncertainty that we have to assume that this is representative, and we don't really know the rate. So we need to find more of them. The other very exciting thing you can do with kilonovae is that if you combine the optical signal with the information encoded within the gravitational waves, you can break certain model degeneracies and learn some really fundamental things about neutron star physics. So the example here, this MTOV parameter, this is the maximum stable mass of a non-rotating neutron star. It's a fundamental quantity in nuclear physics. And if you combine the GW with the optical photometry, the uncertainty in this parameter shrinks by about a factor of 2 with just this one kilonova. So from more kilonovae, we'll be able to pin down fundamental nuclear physics as well as this chemical evolution of the universe. And I promise you, we are trying our best, right? It's been a long time since we got a gravitational wave and a kilonova together, none since 2017. It's been a bit unfortunate. I think we were just very lucky in 2017. It was so nearby. All the ones since to be much further away, much more poorly localized in the sky. But we do a pretty good job following these up. So this is an example of one from 2019 that we think had a neutron star in it. The sky map covers most of the sky, but our ATLAS survey covered a very large fraction of the sky map. And actually, we were able to put some constraints to rule out some of the more exotic kilonova models with this follow-up search. So we're still trying. What's going to be really transformational for this field, of course, is the Rubin Observatory. It's going to have the wide field of view to do this follow-up search, but 5 magnitudes deeper than ATLAS, so you can catch these really faint and fast evolving transients. And with 1 million transients per year in the wide field survey, we should even finally find a few kilonovae just from the wide field searches without a GW or gamma ray burst trigger. So that's incredibly exciting with Rubin. I do want to emphasize the era of small telescopes is not over. So Rubin's going to be incredible, but the cadence is a little bit slow to revisit the same patch of sky because it observes in so many filters. What we need to do is also keep observing with small telescopes like ATLAS and the new LS4 survey here as a good example, where the small telescope gives you this beautiful time sampling around the peak of your transient, and LSST gives you these incredibly deep early time and late time detections that are very constraining for model fitting. So I'm really excited to combine the different surveys together to see what we can learn. And the final thing I'm excited about is our new spectroscopic facilities. 2 new surveys coming online that we're commissioning right now. One is SOX, the Sun of X shooter spectrograph. This is on the NTT in Chile, the successor to PESTO. It's going to do dedicated follow-up in UV to near-infrared high-resolution spectra of many, many transients. And the other is TIDES. So this is on the foremost multi-object spectrograph in Chile. A few % of the fibers we're going to be given over to transient spectroscopic classification. And with these fibers, we expect to get something like 30,000 real-time classifications of transients, more than has ever been done before, and several 100,000 host galaxies. So with this, we can, I think, really pin down the statistics of this population and answer some of these enormous questions that I've been proposing today. So I think I'm out of time. I'll leave up what I'm excited about for the future, and thank you very much for listening.
Thanks a lot, Matt, for keeping up with the time. And now the floor is open for questions from the audience. Let me see. Yeah, there is a question here, just in the front.
Thank you for an excellent talk. You mentioned that we found around 10 kilonovae. Do you remember what is the fraction that we find in star-forming versus non-star-forming regions for these events?
Yeah, it's a good question. It's hard to do with the kilonovae, but you can do it with the GRBs themselves. So it should be the same fraction of short gamma ray bursts. They're quite distributed across the two. I think the slight majority, if I remember, are in the non-star forming, the bigger galaxies, but you find them in both star forming and non-star forming environments.
Are there any other questions in the audience? Don't be shy. Yes, there is one in the back there. Don't be shy.
Hi, I had a question about your version of the supernova transients. So for the massive star ones, does the light curves and the spectra like smoothly transition from one to another, such that like if we want to create models of them, we can like change one parameter smoothly, or are they like discrete from one another?
Yeah, that's a great question. So it seems like these very bright, very massive supernovae probably are continuous with the lower luminosity population. We do find objects in between with timescales also in between. But this strong metallicity dependence only seems to happen for the very, very massive ones. So it's unclear whether there is some thing you just turn on or off, or whether there's a parameter you can dial up continuously. It's not 100% clear whether it's one population or whether the higher luminosity ones are really something different.
Thank you.
Is there another question? Yeah, there is one here. Thank you.
Thanks for the very nice talk. I'm Smaranika from Stockholm University. So I'd like to know that you are discussing kilonova, and I'm also working on this, very exciting. So are you also thinking of like for the collapsers as the R process source and like using Rubin for that, and what's the plan? I would like to know. Thank you.
Yeah, it's a good question. So the collapsars, there have been people searching. Jillian, who did one of those plots, is in the room somewhere too. And this collapsar origin, it's very hard to see because the collapsar is so bright, powered by nickel decay and other things, and the R process is the subdominant source of luminosity. So we need to do more follow-up with the infrared, especially. So Rubin will help a bit because it goes to Z and Y, but I think you need to go further into the infrared. So it's very challenging. What I hope is you can almost do it the other way. If you can actually really measure the fraction that come from kilonova, you find out, do you need another source or not? That might almost be easier. It's hard to say, but for sure we should be looking at other channels and not assume that it's all from neutron star mergers.
Thank you. There may be time for one last short question if there is one. Let me check. There is one here. Thank you.
So you mentioned the superluminous supernovae appear in low metallicity dwarf galaxies primarily. Can you elaborate on the differences between the host galaxies of superluminous supernovae and host galaxies, for example, of gamma ray bursts?
Yes, that's a great question. So I actually think there's a really fundamental connection between long gamma ray bursts and superluminous supernovae, partially because they both come from strip massive stars, but also because they both show this preference for low metallicities, like you say. The superluminous supernovae seem to show it even more strongly than the gamma ray bursts. The gamma ray burst rate seems to drop off pretty sharply when you go below roughly solar metallicity. For these, if you go above even a half solar, the production rate seems to drop off dramatically. So whatever it is seems to be, I think, a similar process to GRBs, but even more sensitive to metallicity than those ones.
Thank you very much, and let you join me applauding Matt. Thank you. And we will now welcome on stage Katie Murray, who's our awardee for the Merak Prize for Early Careers in New Technologies and Multi-Messenger Astrophysics.
So it's a real pleasure to award the 2025 Merak Prize for Early Career in New Technologies Multi-Messenger to Catherine Mulray for her work on the detection of ultra-high energy cosmic rays and neutrinos through their radio signals. Congratulations.
And the floor is yours for your presentation on radio signatures of cosmic particles. If you want me to take the,
oh, yeah,
so that I don't forget it.
Yes, thank you very much for the honor of this award and also for the opportunity to talk about radio signals from radio signatures from cosmic particles. In particular, I'm going to talk about radio signals from air showers or the particle cascades that occur when cosmic particles, in particular cosmic rays, enter the Earth's atmosphere and produce a secondary cascade. So I'm just going to very broadly introduce multi-messenger astronomy in terms of the particles that we can see. So what we're ultimately trying to understand is the type of objects that can accelerate cosmic rays to the extremely high energies that we see. And kind of a back of the envelope way to calculate this is to say that the maximum energy you can reach in a particular type of source is proportional to the charge of the particle, the magnetic fields, and the size of the acceleration region. So in that way, we can kind of understand what types of particles can be produced. Of course, cosmic rays, being charged particles, have the problem that they are deflected in magnetic fields on their way to us, and so they pose a bit of a challenge in terms of pointing back to where they came from. However, they do, at their sources, often interact either in photon fields or with some kind of other matter there and produce gamma rays via pion decay. Gamma rays, of course, are excellent messengers, except for at the very highest energies, we run into this absorption problem. So sometimes they make it to Earth, other times not. And then we also get neutrinos, again with about 10% of the energy of the original cosmic ray. And these come from similar types of interactions at the source and pion decay. Now neutrinos, also excellent messengers, reach the Earth but are very hard to detect. So this is their plus and minus. You can also have neutrino production from another method here, which is where you have an extremely high energy cosmic ray, EEV energies and above, interacting with the cosmic microwave background and producing a neutrino there. So these are the types of particles that work in concert together to inform about their sources. They all come with their challenges and they all come with their benefits. So in this talk, I'm going to focus first on the cosmic ray detection and then at the end return to neutrinos. So in order to kind of place, to figure out where we are in terms of our knowledge about cosmic rays, we look at the cosmic ray energy spectrum here, and there's a lot going on. So what you see is the flux of cosmic rays as a function of energy, ranging all the way from GeV energy scales to beyond EeV scales. At the low end here, you can see these very nice distributions of different mass groups, and that's because these are frequent enough, impinging on our atmosphere roughly every 1 per meter squared per second. So these are totally feasible to detect in a satellite-based experiment. And you can then identify these wonderful mass groups. At the very high energies, you're talking about 1 particle per square kilometer per year. This quickly becomes unfeasible to measure in a satellite. And so this is why we rely on these air showers of particles, which have a much larger footprint in general, to try to detect them. And here you can see there's no longer mass groups that can be split out on a plot like this. Finally, I'd like to mention here, you have this kind of bumpy region. This is where we're not quite sure if the particles are galactic or extragalactic, but this is indicative of changing sources. And I'd also like to highlight that the center of mass energy at the Large Hadron Collider appears around here. So we're really approaching hadronic physics and trying to understand acceleration and interactions in kind of a new frontier, let's say. Right, so like I said, we have basically well understood galactic cosmic ray acceleration at the lower energies in supernova remnants, so Fermi acceleration, et cetera. And at the highest energies, you can make arguments based on energetics that you have to have very large or very strong objects with very strong magnetic fields. So some of the classic candidates are starburst galaxies, regions around black holes, AGN, but this is not well constrained at the moment. And in the middle here, what we call the transition region is where we expect the highest energy galactic accelerators to occur. For much of my career, when I was a student, we kind of said, okay, galactic accelerators are from supernova remnants, case closed. But it's actually becoming more and more clear, especially with complementary observations of gamma rays, that we really don't understand what the highest energy galactic cosmic ray sources are. For example, LASSO has these Pevitron sources with bubbles and things like this, which indicate that the processes are much more complicated. So how can we actually go about trying to solve this problem using cosmic rays? Again, the magnetic fields completely scramble, and these middle range energies, the trajectories. Well, we use this again, this rule of thumb, that the maximum energy is related to the source and the cosmic ray itself. So if we only had, for example, a very simplistic accelerator, let's say something that is accelerating in a rigidity-dependent way, we would say the same source could accelerate an iron nucleus to 26 times that of a proton or a hydrogen cosmic ray. And if that's the case, if there were only one type of source population in our galaxy, what you would see is light cosmic rays start to die out and be overtaken by heavier cosmic rays in the flux as they gain higher and higher energies. And then you could say, okay, maybe we have extragalactic accelerators are going to kick back in. And this is kind of like a cartoon version of how you play this game, but this is the kind of information you can gather if you can measure the energy and the mass or charge of cosmic rays. Slightly more complicated scenarios can be seen here. These are just two. But for example, you could imagine that a Wolf-Rayet star could be a good cosmic ray accelerator. And this could be differentiated from other types of acceleration processes based on a very high helium content of cosmic rays. The critical point to take away here is that the only way to kind of unravel this is to be able to measure specific mass groups in cosmic rays over a large range in energies, and that is the big challenge. So, okay, a little bit of air shower physics, because this is going to motivate all the rest of this talk. Let's say you have an air shower like this. Now, what happens is the original particle interacts somewhere at the top of the atmosphere, produces cascades of millions or billions of particles, depending on the energy. The number of particles in the cascade or air shower is proportional to the original energy of your particle. This is actually a full Monte Carlo simulation where all the tracks basically are showing the different particles in the cascade. And depending on the energy of the air shower or the geometry, you're talking about roughly 5 or so kilometers of shower development. And this is really happening kind of in the near field, in speaking to a room of astronomers. This is like really happening right on top of us. So the actual content of the air shower is mostly electrons and positrons. You also have a population of muons and hadrons closer to the center of the air shower here. One thing that's quite interesting is that the hadronic part of the air shower, in particular the muonic byproducts, is really an open question, especially at the higher energy simulations, and data just do not match up at all. And so this is a clue that we don't understand hadronic physics at the high energies, which is good because it means there's still a lot of work to do figuring this out. And then, okay, so what can we actually take away from this air shower? What do we try to use to reconstruct the composition? Because proton, hydrogen, helium, iron cosmic rays will all interact, produce this air shower, but it's very hard to disentangle which type of particle made which type of shower. So this here is a picture of atmospheric depth, so top of the atmosphere, ground level, and the number of charged particles in the shower here, kind of normalized to a certain point. And what you see is that on average, lighter particles penetrate deeper into the atmosphere before they interact, and so the whole air shower takes place further down compared to heavier particles like iron. So for the same energy, by studying where the air shower develops in the atmosphere, you can make a guess about what the mass of the primary particle was. And the indicator that we use to do this is usually called Xmax, the point of maximum particles. Next slide. Yeah. There are many different types of ways to detect air showers. You can use the particles at the ground level. You can use, for example, fluorescence light. This is what one of the main methods that the Pierre Auger Observatory does. Hess is using Cherenkov bladder detectors. All of these on the edge are dedicated cosmic ray experiments that are built to measure cosmic rays. And here we have LOFAR, which I'm going to talk in more detail about later, which is a radio observatory that we use on the side to detect cosmic rays. So getting into the radio part of this, the radio signatures, where does this actually come from? So as you have your cascade developing, like we said, there's mostly electrons and positrons in there. And so what you have, as these particles pass through the Earth's magnetic field, you have the positive and negative charges separating. This creates a transverse current that's moving towards the Earth at the speed of light. And so this creates a very sharp pulse of radio emission. You also have a secondary effect called either charge excess or Ascarian emission, where you basically, via positron annihilation and gathering more electrons into the air shower as it develops, end up with a charge excess that's also varying in time and moving at the speed of light towards the ground. And so this is basically akin to classical Cherenkov radiation in the optical regime, but it's happening in radio. The mechanics are slightly different. But you get very forward beamed emission that creates a ring. And you can see this is not a symmetric. This picture is a ground view of what the radio fluence would be on the ground. You can see this destructive interference, and that's from these two different mechanisms. Yeah. So what you're actually seeing is, like I said, this very beamed Cherenkov-like emission. The reason it's not a sharp cone and it's kind of blurred out is because the index of refraction in the atmosphere is changing. So rather than having one Cherenkov angle, you're kind of moving, emitting at a different angle as you go down. If you have an antenna right here on the Cherenkov cone, you see this super peaked emission with a very broad band in frequency. If you go closer to the center of your footprint, you have some kind of interesting interference patterns that come from the angle at which you're looking at the shower, and actually we're still trying to figure this out. And if you move outside towards the edge of the footprint, you see that you start to lose some of this coherence in your radio signal. So the point of this is that the radio signals that you can measure on the ground contain a wealth of information about the shower development, and this allows you to then reconstruct these parameters that you need to know. In particular, Xmax. You can see kind of here another cartoon of if you have your shower developing closer to the ground, perhaps induced by a lighter primary, you have kind of a smaller pool of light, more concentrated, versus an iron primary. And you can see also here, if you integrate this entire radio energy that's been emitted, that also is connected to the energy of your primary cosmic ray. So these, this type of detection really gives you a lot of information and has been pretty successful in the last decade or so, establishing this as a real technique going forward. So I want to now highlight a couple different efforts that are ongoing to use radio detection to measure cosmic rays. So at the very highest energies, you have the Pierre Auger Observatory. If you're not familiar, this is the biggest cosmic ray observatory in the world. In Argentina, you can see here, we're talking about an observatory with detectors spanning over 70 kilometers in one direction. So this is just absolutely huge. And again, when you're dealing with fluxes of fewer than a particle per square kilometer per year, or even less, you have to build a gigantic detector to be able to capture these kind of signals. So this is a picture of what it looks like on the ground there, and this is a picture of what one of the detectors at the Pierre Auger Observatory looks like. This is actually just a water tank, and so when particles pass through, they produce light, and this is kind of a classical way to measure air showers. Recently, actually just finishing this year, there's been an upgrade that includes a radio antenna on top of the signal, on top of the water tank, and that's used to basically give you a lot more flexibility in terms of which type of air showers you can see. And we have some first data coming in. This is really just recently finished. And here what you see is the signature of, this is the footprint of a cosmic ray that's extremely inclined. So it's coming in like right along the edge of the Earth. And it's stretching over 60 kilometers, which is just, I don't know how to convey that this is like crazy to see something like this. And so, but this is really cool. And this kind of signal is really only available in the radio because the other particles would get absorbed if they're passing through that much atmosphere at these inclined angles. Also kind of interestingly, a little aside here, at the very highest energies, you can do more or less direct pointing. It's not exactly direct, but at the very high energies, your particles have high enough rigidity that they don't care so much about the magnetic fields in the galaxy and extragalactic magnetic fields. And so you actually do see, this is the arrival directions of cosmic rays at the very highest energies. This is the galactic plane, the galactic center, and you see that you see more particles at the high energies pointing away from the galaxy, which is another indication that these are actually extragalactic. This is tricky. There is still some bending, so you can't point back exactly, but this is also a nice indication that we understand at least the classes that we're looking at the high energies. LOFAR, this is actually the project that I moved to Europe to work on when I was a postdoc. LOFAR, of course, is a radio telescope used for many purposes. And we found that it actually makes a brilliant cosmic ray detector just because you have many, many antennas in a small area. And you can plug in kind of to the system on a low level and use it to also measure cosmic rays. This is probing. Now we're not talking about Auger scales, we're talking more about like roughly square meter or so in the core area. And so we're talking about probing energies in the middle of this transition region. So these are some of our event displays at LOFAR. What you see here, if you're familiar with the LOFAR SuperTerp, you see the different antenna fields, high band antennas, low band antennas. We primarily in the past have only used the low band antennas for detection for some technical reasons. But what you see here is in the background a full simulation of what the radio footprint should be. And in the circles, you see the integrated radio signal from individual antennas. And what you see is that this high density of antennas allows you to constrain the simulation very well, and that then allows you to say what kind of cascade development we had. And indeed, that's what we have here. So when you do these kind of studies, you end up with a plot that shows X max. Again, this is a proxy for composition as a function of energy. If you only had proton cosmic rays, hydrogen cosmic rays, you would end up on this line. If you only had iron cosmic rays, you would end up on this line. And so any deviation says that you're in some kind of intermediate mass group. And what's especially interesting is the how this changes over energy. And this is exactly what we're looking for. We're looking for trends to heavier or lighter types of primaries to tell us about when some of these source classes might cut off. This also shows how you can break down individual mass groups with LOFAR observations. So these plots are great, but they also show the challenges that we're dealing with. All these different points come from different experiments. You can see that there's no general agreement, I mean, maybe broadly speaking, but it's very hard to combine this information from different detection techniques, from different observatories, and over different energy ranges. And moreover, you can see here where the uncertainties in hadronic physics start to enter the picture. You have every time 3 different scenarios. These are 3 different hadronic interaction models. These lines are all 3 different hadronic interaction models. So at this point, any kind of interpretation of the data is starting to run up into this problem. I'm looking forward to LOFAR 2. So this is going to be the upgrade that's happening to LOFAR. This is going to really help us hone our detection there. In particular, what I'm looking forward to is that we'll be able to measure in a broader frequency range. So this is the same figure of what the frequency spectra in one antenna looks like. LOFAR probes this region. LOFAR 2 will be able to probe this region, and so you're covering a lot more frequency band, which then allows you to probe different parts of the air shower development. And of course, if we're talking about radio detection of cosmic rays at radio telescopes, the ultimate goal is to measure them at the SKA low as well. For starters, this will open up a very wide energy range for us to measure in. If we just do a direct comparison, this is what an event might look like at the positions of the LOFAR antennas. This is what the same event will look like at the position of the SKA antennas, where of course each one of these points is actually 256 antennas. So you also have way more antennas, you have huge coverage of the field, and you also have a very wide band to measure in. So now you're really covering the entire frequency spectra that we're interested in for cosmic ray measurement. This will really allow us to reconstruct air showers so well that we'll be able to identify individual mass groups. But there's more interesting things we can do. This is kind of a fun application. This goes back to the question of hadronic physics. How do we start to improve our hadronic physics models at energies above what can be produced in the LHC and confirmed? Well, nature is giving us a source here. It happens, depending on what energy you're talking about, a few % of the time, that you get an anomalous air shower. For example, you can have an interaction where your nucleus splits fragments like this. One part proceeds as normal and produces a shower, and one part then goes way deeper into the atmosphere and produces another shower, and you get kind of this double shower effect. If you can measure this, if you can measure the relative development of both showers, you can understand something about the cross sections, about the particles that started this whole thing. And this leaves a very distinct signature on the ground. Here you see a Cherenkov cone from one shower and a Cherenkov cone from the other shower. Very cool. This is, of course, simulation, but we could only possibly try to probe something like this if we have complete full coverage like you would at the SKA, and also a wide measurement bandwidth. So this is really great. And then I also just want to mention, we think that it's going to be possible to measure gamma rays also at the SKA. Gamma rays, of course, also produce these air showers and produce radio emission. The trick is that it's very on the low end of what's possibly measurable. At the SKA, you have so many antennas in a field, you can start to do more beamforming. We don't usually do this in cosmic ray physics, but this is possible. And so we hope that we can, there's a lot of technical challenges. So this is not something that's going to happen tomorrow, but this would be really nice. So this is what I'm most excited about going forward in the future, and we have a large group actually actively developing the technologies to try to make this happen, especially via support from NOVA in the Netherlands. Now, at the last few minutes here, I want to also talk briefly about technologies to use the same radio techniques to probe neutrinos. So we're in basically the beginning stages of the era of neutrino astronomy here. This is a galactic center and different messengers, and then here at the bottom, produced by the IceCube Observatory. If we look at the actual neutrino flux here from IceCube, you can see an astrophysical flux ending around 10 PeV. And this IceCube Observatory uses optical detection in ice. Of course, we also have this very intriguing event from KM3net using optical detection in the Mediterranean now, which has a very high energy event. I would say the limitation with both of these approaches is that using optical detectors, your Cherenkov photons from your cascades get absorbed. And so you can't really easily instrument a large area. So we would like to try to use radio approaches to try to do this as well. If you have radio waves in a dense medium like ice, they can travel for kilometers, whereas Cherenkov photons 100 meters or so. So it's exactly the same process. Rather than an air shower, you have a particle cascade developing in ice. It just happens on much smaller length scales here. And so you have much higher frequency content. And there's a number of pathfinders already trying to work to get prototyping to see how this can be done in ice. And in particular, I just want to tell you about one, RNOG, which is being built right now in Greenland. Greenland has beautiful ice for radio detection. It's very cold, very deep, so great for propagating long distances. And there's also a facility there that you can use to get some kind of infrastructure. So the concept is you have antennas in the ice, you have your neutrino interaction, and your radio emission, because of the changing index of refraction in ice, has a couple different paths to travel to your antennas, and then you can use this for reconstruction. In practice, deep here means 100 meters or so. You have vertically polarized antennas, horizontally polarized antennas, some surface antennas, and you use the phased beam approach, so you can kind of point to more optimal places in the ice where you might see a neutrino. Just a couple pictures of what the deployment looks like. You have to dig the holes, of course, and this is done using a drill, which is hidden under this white tent here, and dragged around by one of these Arctic vehicles. You can see a hole here in an ice from many centuries ago that you can put in your drink. Once your hole is drilled, you bring this little deployment hut on a snowmobile over the hole and then proceed to deploy your instruments there. And one thing I really like about these kind of experiments, these pathfinders right now, is they're small enough scale that, I mean, students, postdocs, anybody who's interested in the project can really join this project and get your hands dirty and put cables together, things like this. And then only then do you really understand the value of getting systematic uncertainties under control. So the goal here is to instrument, to build 35 of these stations. This is a picture of the completed station. Of course, it's all under the ice, so all you can see is the flags where the holes were, and solar panels to keep it going. We haven't seen any neutrinos yet, no surprise, but there's a couple backgrounds that are interesting to track and prove that the system is working. For example, this project has seen solar flares. You can track airplanes across the sky. So while we wait for the ultra-high energy neutrino to hit the ice in Greenland, we can get everything under control with the rest of this. And then ultimately, the goal is for this to become merged into some of these larger projects at like generation 2 of IceCube. So I'll leave it there. I'm really excited about what we're going to do in the next 10, 15 years with radio detection of cosmic particles.
Thanks a lot, KP, for this exciting talk and for keeping up with the time. And now the floor is open for questions from the audience. Again, don't be shy. Do I see any hand raised? Yeah, there's one there.
Thank you very much. It was a very comprehensive talk and very clear, very nice. One of the difficulties that exist in this field is the triggering, right? And you mentioned that in one of your slides. So I'm pretty familiar with the perspective from the Auger point of view, but what's the perspective for LOFAR 2, for SKAO? What will be the frequency ranges of interest for triggering or the techniques? How do you see the future for this?
Yeah, this is a very important point. What we've done at LOFAR very successfully is we've actually used the particles on the ground level to trigger. So we have an array of particle detectors on site at LOFAR. The radio signal is buffered for a few seconds, and then we form the trigger with the particle detectors and then send out a signal to stop and read out the buffers. This works well because there's no background in particle detection. I mean, all you can do is just detect another air shower. So that's what we've used at LOFAR. That is also the primary plan for what we do in LOFAR 2 and SKA. Of course, there are big challenges there. You have to build a particle detector that has 0 radio emissions and things like this, because there can't be any background, and getting all that infrastructure in place. But in general, that's the idea. We could also think about triggering on the radio itself, but in a facility that is, we can't tinker with, let's say. I think the more stable thing to do is to use the particles.
Thank you. Is there another question in the audience? Don't hesitate to raise your hands. There is a question by Lucio. No, it's okay. No. It's streamed.
So I have a naive question just out of curiosity. You showed that the sensitivity is improving, so you're being able to detect lower energy particles produced in the shower. But I guess this becomes also more difficult from the data analysis point of view, because you might have also overlapping events. And just wanted to hear what you think about the analysis part in the future.
Yeah, indeed. Overlapping events, that's an interesting point. I don't think at these energies that we actually have to worry about that yet. If we see 2 events at the same time, they'll be separated enough in time, and we have the information from the particle detectors that we can share this out. The nice thing is that we can dig out low energy events from noise levels, essentially, and the galactic background is our biggest background source, because we'll know exactly the timing of the event, where to look for the signals. We have a pretty good idea of what the shape of the signals is, and so in that way we can use template searches, things like that, to try to find this.
Thank you. Are there any other questions? Do I see a hand? Oh, yeah, sorry.
Hi, thank you very much for the talk. So you mentioned that the facility in Greenland is particularly good because of the quality of the ice there. So as global average temperatures sort of increase due to climate change, and that may affect the quality of the ice, do we expect that to have much of an impact on the capability of the facilities and the quality of the data?
Yeah, this is always something that is concerning and in the back of everybody's mind. Indeed, warm temperatures make ice warmer, and so the propagation of radio waves goes down. Also very difficult at these kind of facilities is that these facilities were designed and built assuming that ice will always be there. Water will never melt, let's say. The temperature will always be below zero. So there's a lot of things that don't anticipate getting wet, for example. And so this can be a huge problem when you've designed something to be basically not needed to be waterproof, and then all of a sudden you have melting. Not to mention melt layers get into the ice, get buried, cause weird modes of propagation. There's all sorts of things that can go wrong. So yes, this is something to think about.
Thank you very much. I'm afraid that we cannot take another question, so thanks a lot, Katie. And I'd like first to have an applause to all our awardees. I mean, they were really great. If I can have one additional couple of seconds, is just to advertise for the next round of the MERAC prizes. So these are prizes for the PhDs. The PhDs have to be nominated, so please do not hesitate to nominate. Last time we had about 55 nominations, so please don't hesitate to nominate your PhDs or ex-PhDs or PhDs that you know, keeping in mind as well the parameter of diversity, geographical, gender, and all diversity included.
Yes, so I also have a very quick reminder for all the MERAC awardees of the past and also the future. They also are entitled to ask for a project grant. Sometimes this is forgotten. The project grant can be 2 times 50,000 K, so they have this opportunity. And after 6 years, in principle, it's not possible anymore after the 6th year following your award. So please, for those who have been awarded in the past and also the future ones, remember that you have this opportunity. Then I also wanted to very quickly mention that this year the MERAC Foundation launches the second George Lake Technology Innovation Award. We had the first call in 2023, so this is the second time. And this is not a prize, it's a project grant offered by the foundation for an amount of up to 100,000 euros. And the idea of this is to promote new ideas in computational modeling, computational astrophysics, data analysis, including, of course, machine learning and AI, and also new techniques in instrumentation and software in astronomy, astrophysics, and cosmology. So please think about applying. It's for a wide career range from the PhD up to 15 years following the PhD. The call will be advertised soon on the MERAC website and on the EAS website, and the deadline will be around mid-November, probably the 15th of November as it was in the past. So that's a new opportunity, that second time, and I hope that many people will apply. Thanks again.
Okay, so after those fantastic prize talks, so my name is Morgan Fraser, I'm the chair for the second part of this. It's my pleasure to introduce Andy Fabian, who will be giving our final plenary talk of the day, speaking about the X-ray astrophysics of the hot and violent universe.
Thank you.
Thank you. Okay, this is the center of the Centaurus cluster, the galaxy NGC 4696 in the middle, towards the nucleus, and I'm going to get to that in a while. What I want to talk about are some aspects of X-ray astronomy at the moment. I'm going to concentrate on the extragalactic sky. This is an XMM image of a chunk of the sky, and what you see it shows us is lots of little dots, and sort of 90% of those dots are accreting black holes in the centers of galaxies, and the fluffy red things are clusters of galaxies and groups of galaxies. So that's what I'm going to carry on talking about. In terms of clusters, let me take you through some of the old stuff and some of the new stuff. You can classify clusters in roughly 2 parts, in 2 types. There are the cool clusters, which have got an in-surface brightness. This X-ray surface brightness rises very steeply towards the center, and the non-cool clusters which just have a sort of small bump. And this is the coma cluster, this is Abel 478. They essentially have the same luminosity, but they're quite different in the center. The cool core ones are getting cooler towards the center, so the temperature is dropping. In order to support the weight of the overlying gas, the pressure is rising, so NT rises. So as the T goes down, N goes up. The emission is mostly Bremsstrahlung, which is a two-body process, so consequently you get a steep rise in the surface brightness. You can measure the cooling time of the gas here, and this is from a student's work. This is the distance from the cluster center in kiloparsecs, 100 kiloparsecs, and it starts out above a Hubble time, but as you go in towards the center, the time is dropping down below, down towards 10 to the 7 years in these, and they roughly have the similar shape. So basically the gas is cooler here, and therefore there's energy being removed, so you expect the gas to slump inwards. The cooling gas should flow inwards at large rates in rich clusters of the order of hundreds of solar masses per year. And what then happens to it? And this is the concept of the cooling flows, which was introduced in 1977 by a couple of papers, Cowie and Biddy and Paul Nelson and myself. And I wrote a review about it in annual reviews in '94, if you want to catch up with that. So cooling flows, what are they? They're something that happened a long time ago, introduced about 40 years ago, and then it sort of died in about 20 years ago, and I'm reviving it. I'm going to tell you why. Here's the Perseus cluster. NGC 1275 is the central galaxy, and you can see something special about it. It looks a bit like a squash spider. These are other elliptical galaxies in the cluster, and that's telling you it's something special. If we go into the X-rays, you can see it's got all this, much of the X-ray emission is centered on it, and there's something happening to this. Now, there's an enormous peak of X-ray emission, and what we're looking at, we've taken away the big peak and just looking at the details, and you can see that nucleus is just here, and either side are these holes, or cavities, or bubbles, and then there are some more bubbles either side like this. And basically, the jets from the black hole at the center is causing bubbling at the bottom of this potential well. The bubbles are radioplasma and then buoyant and rise outwards, and that accounts for those. And you can see it sitting in the cluster, and you can see other elliptical galaxies as X-ray sources. Here's a close-up of the center there. The radio emission is filling these cavities in the center, and surrounding them is a sort of brighter patch of harder emission, which is a shock, a weak shock that's surrounding this region. So the bubbling is pushing out, and it's a bit like I think like a fish tank aerator, sort of blowing bubbles, except in one each side, and they're rising up in the cluster. And this led to the idea of AGN feedback in clusters, and this is again the Perseus cluster again, but you can see these pairs of bubbles in other clusters like over there. And when one works out what the heating rate or energy input rate from this bubble is, and that's called the cavity power. We can work that out because of the fact we've got the size of these cavities, these holes. We know what the pressure of the gas is in the center from the X-ray observations. So P times V is the energy, and we can work out from physics a sort of buoyancy time, and then therefore we've got an energy and a time, we've got a power, and compare that with the X-ray cooling luminosity. That's the loss of energy that the gas has because it's emitting the X-rays we see, and you compare it, and it's, for astronomy, it's not a bad correlation, but do notice there's a big spread because that's important later on. But this led to the concept of AGN feedback, and I wrote a review about that as well, and it looks like the whole thing is sort of bubbling away, and it could be that the cooling loss of energy is compensated for by this power from the cavities. So maybe stuff isn't cooling after all. But a big issue is how is energy transported in the cluster? Is it due to turbulent motions or could it be sound waves? I prefer the second one here, and I'll get to that later. Now, what we want to do is, this stage, is I want to look at how you can measure the motions of gas in the cluster. And the first, what you need is a very good spectrometer, being able to measure velocities of tens to hundreds of kilometers per second. And in 2016, the Japanese-US satellite Hitomi was launched, and that had on it a microcalorimeter operating at 50 millikelvins, and that gave us this spectrum of the Perseus cluster, which I keep showing you, and it measured the line widths. You can take away the instrumental width and look at what's left. The dispersion of the energy, the dispersion of the velocity is about 160 kilometers per second. So this is a very low velocity, and if you compare it with sound speed, if this gas is 1,000 kilometers per second, it's highly subsonic and means there's low turbulence in it. And the turbulent energy in this region is only a few percent. Recently, 2 years ago, just less than 2 years ago, a new microcalorimeter experiment was launched called PRISM. I want to talk about that. And that gives similar spectra. And here it was able to look at the coma cluster. The coma cluster is not a cool core cluster. It's undergone a major merger. And looking at the coma cluster, there were two pointings, the north and the south pointings. And what was seen there is the bulk velocity is minus 450 there, minus 730 there. So there's a large shear across the core of the cluster in terms of velocity. But if you look at the velocity dispersions in each of these, they are around 200 kilometers per second. Now, this is very interesting because it's telling us, again, that turbulence is very low in this cluster, which is undergoing a collision. And these are the spectra, and you can see how sharp the lines are, you can measure them and so forth. And this is a very important plot I'm going to show here, and that is, it's a ratio of kinetic to total pressure. It's taking the kinetic pressure and comparing it to the kinetic plus thermal pressure, or energy density, and it's only 3% in the coma cluster, the kinetic pressure. And that's very low, and these are simulations, numerical simulations of clusters, where the results have been gathered, and you can see most of them were predicting of the order of 10%, and only a couple of them are showing things that are down at a few percent. So that's waving a flag that maybe the numerical simulations of clusters aren't necessarily getting it right. And also, it's showing us that it's not Kolmogorov turbulence. This is from the paper that's come out from PRISM, and these are rather complicated plots, so I'm not going to dwell on them for long, other than to show you, look at this is the velocity, whatever velocity we're looking at in kilometers per second versus wave number. If you work on turbulence, you will use inverse length, so that's kiloparsecs to the -1. And this is what is the Kolmogorov idea is in turbulence that you have worlds that have lesser worlds feeding on them, feeding on their velocity, and the lesser worlds have smaller worlds, and so on to viscosity. You probably have heard that poem before from Richardson. Okay, so you churn the gas around, and the worlds that you create make smaller worlds, and they keep going until they reach a dissipation level, and that's where the energy flow is taking place. But that's what the Kolmogorov slope is. But if you try and estimate what it is in coma, it's much more like this. It's much steeper. Namely, there's lots of large-scale power and very little small-scale power. And I'm dwelling on this, and I don't like these plots. But take it from me that it's a very important result in terms of what's going on here, because it's saying it is not Kolmogorov turbulence, and we've got to think again about what these large bodies of gas, and bear in mind, we're dealing with the largest bodies of gas in the universe. Clusters of galaxies are the most massive bound systems in the universe, and most of the gas in them is actually in the intracluster medium and not in the stars in the galaxies. Go to another cluster, Hydra A, where here you can see, this is where the radio source has blown cavities either side. You can see them with a little difficulty in this Chandra image here. And this is another picture on a larger scale. This is 190 kiloparsecs. And CRISM has looked at that and measured the velocity in that object. It's a very hot cluster. And the answer is 164 kilometers per second. Again, a very low turbulence or kinetic energy. And just to give you some equations, if we want to think about kinetic energy versus thermal energy in the cluster, you can play around and look at the ratio of the two and compare it with the radius of the cool region you're looking at and the cooling time, and deduce the velocity that's required if you're going to use turbulent energies with velocities similar to what we measure. If that's being dissipated and you're transporting energy outwards in the gas, it's easy to see that the velocity required is more than 540 kilometers per second, but you're actually measuring 164 kilometers per second. So basically, the velocities are not high enough to transport the energy around in the cluster in order to compensate for the energy loss due to radiative cooling. I like the idea of sound propagation. As I've shown you before with the plots, you can see there's ripply structures in the images. And an interesting thing about sound is the sound propagation is at 1,000 kilometers per second in these objects typically. But the velocity with which that you measure, if you're looking at vibrations in it, you're measuring the displacement velocity amplitude. That's how much the particles are being displaced coherently with the sound wave, and they're quite different. So, for example, if I talk very quietly, the displacement velocity is small, and if I shout, the displacement velocity is large. And if I shout very loud, then eventually it gets to the sound speed and we get a shock, but I can't do that. But you get the idea that that's how it's working. So therefore, if you have sound waves going through a cluster, they can be transporting energy at 1,000 kilometers per second, but you don't measure the 1,000 kilometers per second, you measure just 160 kilometers per second. So that's one possibility of what's happening in clusters. It won't be the first time that acoustic energy is working in cosmology. Most of you know about baryonic acoustic oscillations, and that was way back before recombination. That's all you had for action going on in the universe. So having sound waves in the universe isn't a silly idea, and everybody knows that in space nobody can hear you scream. But the thing is, there's still gas there, and if you scream at a very low frequency, and it's extremely low, then you can do that. Anyway, now I want to look at, is the gas cooling? Something like 20 years ago, this plot is just slightly more than 20 years ago, from the XMM satellite, you're looking at the reflection grating spectrometer, which is the data there, and this is a plot of what the cooling gas should do in terms of producing the spectrum. You expect to see these lines, sharp lines due to iron 17, which are characteristic of gas at about half a keV, and they're clearly missing from this. And this was characteristic of quite a lot of the cool core clusters. And I and others were led to believe that no, there is no cooling taking place, and so cooling flows were sort of pronounced dead back then. But I've always sort of hung on thinking there's something wrong with all this. And looking at the Centaurus cluster and coming to the amount of mass cooling rate, so it looks like we're not seeing enough gas to show a constant cooling rate. But actually, is it the gas that's missing, or is it just the luminosities that's missing? And you can get rid of the luminosity by putting cold gas in the way and using X-ray absorption, photoelectric absorption. So can the decline in mass flow be explained by photoelectric absorption? And I picked this up after I started thinking about it during the pandemic, and have picked it up afterwards, and I pressed ahead. And I call it hidden cooling flows, just because of the fact they've got absorption involved. And include absorption of soft X-rays by cold gas, but it's got to occupy the same region as the cooling gas. And I use a model we developed some years ago for something like this, and essentially the energy that's being absorbed can come out emitted by dust and gas in the far infrared part of the spectrum. Here is the Centaurus cluster, the one I showed you right at the start and also briefly just now. This is what the RGS spectrum looks like. And yes, you can clearly see the iron 17 lines, and there are other lines, and this is oxygen 8 and so forth. But this is the fit I get to an absorbed cooling flow, and I conclude a mass cooling rate of 16 solar masses per year. And this is a cluster where the central galaxy, which we look at, has got a star formation rate that's less than 0.01 solar masses per year. So it's not going into star formation. This is what the center looks like, and I don't have to do much work to persuade you there's some absorbing gas present. And if you look up there, this is just a different tweak on the Hubble image, and you can see there's gas all over the place. And this is from Herschel, observations in the far infrared. There's a big bump there, and that bump, the luminosity in that bump equals the amount that is absorbed from the X-ray cooling. So we find this working in many clusters, and you can see evidence for absorbing gas in these ones. The big issue, and this is where we get to the stumbling block, is how much gas accumulates. If you have 16 solar masses per year or 10 solar masses per year, in a gigayear in Centaurus, you get 10 to the 10 solar masses of cold gas. The molecular mass measured in it is 10 to the 8. So there's a factor of 100 problem. It turns out to be 10 to the 11 solar masses in Perseus, which does have a lot of cold gas, but not that much. But what is too much? Are there lots of very cold clouds? And I'm going over to the idea that it means there's low mass star formation, that maybe in the very high pressure environment at the centers of these objects, where the pressure, NT, is bigger than 10 to the 7 per centimeters cubed Kelvin, the gene's mass goes down and you actually form just low mass stars. It was an idea first put out by Mike Durer in 1977, but we've pursued it a bit since. And it's interesting that many people using optical infrared observations of nearby giant ellipticals like Van Dockum, and there's Oldham and Auger, and a paper by Jenny Green and co. They find there's a bottom-heavy IMF observed in nearby ellipticals. And I'm arguing that that is due to this process. Here's Perseus in the H-alpha HST image, and it doesn't look as though it's very turbulent, does it? I mean, you know, going from there to there is 50 kiloparsecs, and I don't think it looks very turbulent, but that's just showing you there's lots of cold gas in this object. This is cold gas plots from ALMA. This is in Abel 2597, where you can see there's absorption against the nucleus, so it's close in. And what I've done is to compare the cooling rates that we work out from Chandra images of large scales, say roughly 50 kiloparsecs of clusters, versus what I find from looking with the XMM RGS cooling rates, and compare the two, and plotting them like this. Then for the ones which have high mass cooling rates, there's quite a range of ratio. It goes between 1 and 20 or so. This means feedback isn't 100% efficient, and heating's winning in some and cooling is winning in others. At low rates, you find that basically cooling is winning all the time. These are some dramatic objects. And just a few things that we find that there are cooling flows common in most massive elliptical galaxies, and we have a paper on that last year, and there's a possibility of testing this idea with JWST and a neon 6 line. Now going to spend the last few minutes talking about the AGN, and let's go through. We've got an AGN at the center, say, and it's got a corona which is illuminating accretion disk, and it's reflecting X-rays out to the observer. If we've got emission lines from the accretion disk, we can make use of the way in which they get distorted by the strong gravity, the large velocities and the gravitational redshift, etc. And we get these skewed lines are predicted. And this is what you get if you get a reflection spectrum. You get the whole spectrum is blurred. This was a result from 1995 with ASCA showing a broad line from MCG as a galaxy AGN MCG 63015. This is what CRISM is now showing for the same object. You can see the broad line, that's this bit. There's a narrow fluorescent line as well. And what New Star is providing is that seeing what we call the Compton hump at higher energies. And that's a very nice fit to the whole spectrum. Laura Brenneman is about to submit a paper on this showing the whole spectrum. So CRISM and combined observations are all demonstrating that this all makes a sensible result. And this object, MCG 63015, has essentially a rapidly spinning black hole, because we can measure the spin by looking how much broadening there is of the line. This is just a general plot of black hole spin versus black hole mass from Julia. And sometimes we see emission from within 2 Rg using this method. You can see this is in Markarian 335 about 10 years ago. You can see the blue is the unblurred spectrum, red is the blurred spectrum. That means relativistically blurred with gravitational redshift and velocities put in. And you can see that fits the data. And it implies that we're seeing in the X-ray spectra, we're seeing down to 2 gravitational radii around a rapidly spinning black hole. And that's well inside what the EHT images, fantastic images they get of the M87 and the galactic center, but we're looking inside that region they're looking at. This is just the similar sort of spectrum from a neutron star source, Serpens X1, where the innermost radius is found to be around about the around the ISCO, expected for a non-spinning black hole, a non-spinning neutron star at around 6 gravitational radii, and it's got a double peak, and that's because that's the helium-like line and iron line, and that's the hydrogenic iron line. We've also started to go and look at the plunge region. This is the point of no return, and we're starting to see emission from that region. But if you want to look any further at that, you'll have to look at the archive and other papers in work with Andy Mummery from Oxford. So that's all the results I'm showing you. Just to talk about the possible future of X-ray astrophysics. This September, there's going to be an attempt to open the gate valve on CRISM. CRISM has got this microcalorimeter operating at 50 millikelvin, okay, and it has a valve on top, a gate valve, so that they could test it on the ground, and because it's a vacuum inside, okay. So after launch, they tried to open it, and it hasn't opened, and they've tried 3 times to open the gate valve. Now, the gate valve is a slab of beryllium with a grid of steel holding it in, and the whole thing is somewhat jammed. They think they only need to move it 1 millimeter in order to get the gate valve to open. because it's got a spring as well. So let's hope that it does open when they're going to try and warm it and shake it as hard as they can. But they don't want to shake it so hard as to damage anything. So keep your fingers crossed that it does open. And then essentially the effective area doubles, and also the soft X-ray band is available. Late 2025 to 2026, I hope there's going to be 3 more legacy megaseconds of Chandra on the Perseus cluster. I and my team won one of those legacy projects. There's a problem, though, with Chandra, and that is because it's from NASA, and as you know, we don't know what the NASA budget is. I don't wish to go into the details of that or anything other than, you know, if we're very lucky, they'll say, let's keep supporting Chandra, in which case I'll get another 3 megaseconds on Chandra, and then we'll know whether it's sound waves or not. Continual operation of XMM and New Star, fantastic. They're both operating beautifully, and long may they do so. We're also hoping that NASA will select an X-ray probe, namely AXIS, which will be a telescope with 1.5 arcsecond resolution, and also a large collecting area, sort of several times that of Chandra, for 2032. But again, we don't know what NASA's going to do. I can only say we can, prayer and fasting is probably about the best you can do. And in 2037, however, ESA's new Athena, we hope that's going to be adopted in 2027, and will go ahead and be built, and that will have a large collecting area, high spectral resolution, and that launches. So that just gives you, that's why it's a possible future rather than this is generally what's going to happen. So thanks very much for listening.
Thanks for that fantastic talk and a fantastic CRISM spectra as well. So do we have some questions?
So it's a very fascinating talk, Andy. When you're talking about the low end of the IMF sort of forming at high pressure regions,
Yes.
Does that mean that you would also predict a spatial variation in where you would have the low, you know, the bottom heavy IMF, because the cooling would be more concentrating towards the center of a cluster, right?
That's exactly where I think it would be. It would be within the inner kiloparsec. So, and there is evidence in massive elliptical galaxies that there is something different at the bottom of the potential well. We are talking about the most massive galaxies in the universe, and a very special part of them. I'm saying the IMF is different. However, I'm fully aware that astronomers don't like to touch the IMF. It's sacrosanct. You can't say it's different, because if you're allowed to say it's different, then you can throw most of the things out the window. But I think this is one place where we do need to change it.
Do we have more questions?
Everybody's hungry.
Yeah, with respect to that Kolmogorov turbulence
Yes.
plot, I was just wondering whether it's possible that magnetic fields might suppress the sort of small-scale turbulence, if that's something that's been investigated.
Interesting comment, indeed. Magnetic fields are around in these, but they are weakly magnetized. There's beautiful LOFAR images of Perseus and other clusters, and where it's been measured in 1 or 2 clusters, Faraday rotation indicates you're talking about microgauss fields. So how exactly they would be strong enough to modify it a lot, I don't know. But I'm sure we're going to hear a lot about this over the next few years.
Probably have time for one more quick question before we break for lunch. Or, if not, let's thank Andy again.